So, hello everybody. My name is Alexey Potapov. On behalf of the organizing committee, I will say a few words about the series. Welcome to the Global Astrochemistry Lecture Series. This is the second round. The first one was in summer semester 23 and was very successful. So that's why we have decided to continue and to expand it. This time you will have more lectures, 18 instead of 14, and more lecturers, 17 instead of 14. So I hope the series will be interesting and useful. And one wish I have to you is please don't hesitate to ask questions. Use the opportunity to talk to interesting people, to world-leading experts in astrophysics, astrochemistry, and biochemistry. So enjoy. Thank you. With this, I give the word to Dr. Sergey Krasnokutsky, who will be your moderator during the series. Sergey, please.
Yeah. Hello, everyone. My name is Sergey Krasnokutsky. Yes, I will moderate all lectures except the next one. And now I will give the floor to Arisa, who is from our technical supporting team and who would report about some technical procedure which we should follow. Please, Arisa, floor is yours.
Thank you, Sergey. I'll be brief. Just a couple of things from the organizing team. We just want to highlight like a couple of things. The first one is that we have created a Slack channel for the course. This channel serves as an additional tool to ask questions, as Alexei said, and share information between lectures. It is not compulsory at all. So during the lectures, you can use Zoom's chat, and then between lectures, you can use Slack. Channel is hashtag GALS2024, and we will be sending you all invitations to join after this first lecture. Then the second thing, it's just to remember that we would be really glad if you could accept the invitation to the course on eCost, the platform, and or register on the platform if you still haven't done so. And even though it was explained in the invitation email, please keep in mind that because of logistical reasons, you will receive 2 more invitations for GALS 2 and GALS 3. But just to keep it in mind, because that will be sent, as I said, later on. And then also, if you could do during the session, it would be nice if identify yourself with your name, surname, and country of affiliation, because that way we can check the attendance. And also the last thing regarding the attendance is that remember that in order to have the certificate of attendance, you need to attend more than 75% of lectures, is 14 lectures, and also the connection time must be more than 75% of the lecture, which is about an hour and a half. And that would be all. Thank you, Sergey. I'll give you the floor back.
Okay, thank you, Arisa, for introducing this procedure. So we are coming back to our lectures, and today's lecture is Alexey Potapov from Max Planck Institute for Astronomy in Heidelberg. He will give an introductory lecture about the basics of astrophysics. So Dima, please, floor is yours.
All right, thank you, Sergey. I hope you hear me well. The goal of my lecture today, in essence, is to introduce you some basic and key information about molecular astrophysics, because I won't be able to cover the entire astrophysics in just 2 hours. And this is the brief overview of the lecture. I will, as I said, introduce the basic concepts, nomenclature, some limitations, and the power of techniques, and so on and so forth. Mainly, that's my main goal. And then I will mention very briefly, because that would be like a teaser for all the other lectures in the course, except of the last lectures about origin of life, about biophysics, which I will not touch. So I will talk a little bit about the formation of the elements right after the Big Bang, and then the first molecules in the early universe. And then I will be talking about the cosmic life cycle of matter in the galaxies, including our own Milky Way. And this is because this stuff is closer to us. We can observe it and see more details with the telescopes. And then I will also be mentioning through my introductory lecture various observational techniques used to study various cosmic objects, as well as various modeling approaches and experiments. But first of all, a few words about myself. I'm originally from Russia, from northwest corner, from St. Petersburg, where I got my university degree in astronomy and mathematics. After that, I moved to do my PhD study in astrophysics to Jena in Germany, to the Friedrich Schiller University, where I got a degree in 2005. And after that, I became postdoc and then staff member at the Max Planck Institute for Astronomy in Heidelberg in Germany. My main scientific interests are theoretical astrochemistry. So I'm a theorist. Well, at least in the beginning, I was a theorist. Now I'm also working more and more with high quality observational data mainly from radio telescopes operating at millimeter, sub-millimeter wavelengths. And I'm using these things to try to better understand how star and planet formation processes work. And another scientific hobby that I do in my kind of limited spare time is the origin of life topic, or more precisely, the formation of life building blocks in space. And besides science, I have a range of hobbies, which range from hiking in the mountains to walking in the nature, photography, cooking, and a lot of other things. Please feel free to ask me questions about the lecture or other topics related to astrochemistry by using my email I show here, or by contacting me via Slack. All right, let's go. What is astronomy, astrophysics, and what is astrochemistry? Especially the last term is a bit misleading, or may appear a bit misleading, because it's astro and chemistry. And actually it was unclear even for the brightest astrophysicists in the past, like Sir Arthur Eddington, who in the beginning of 20th century coined this very famous phrase, atoms are physics, but molecules are chemistry. And some of my astrophysics colleagues still think that way, because chemistry is complex and molecules is hard topic to study beyond all the complexity of astrophysics itself. So molecular astrophysics or astrochemistry, and I will use these two terms interchangeably during my lecture, is the study about formation and destruction of molecules in the universe, and how they interact with radiation, and what kind of feedback they could provide on the physics of the environments they sit in. It's an interesting field, but very complex, because it is interdisciplinary field. One has to know something about the physics, as well as chemistry, as well as astronomy, and maybe biology if you're interested in the origin of life stuff. So it's a hard, challenging task, to get all the knowledge needed to understand stuff. It sits on the three cornerstones. In essence, astronomy is observations dominated science, and so, but this observational data, they have to be kind of explained and understood, and we do it by performing advanced theoretical modeling as well as laboratory studies, and these are the three cornerstones of behind astronomy as well as astrophysics and other sciences. All right, so that's regarding the definition of astrochemistry. What about the interstellar matter? Here I refer to the interstellar matter as something that sits between the stars, and mainly the stars that are not that far away from the sun, as I said, that because we can understand this stuff better because we can see it better with these telescopes. The main component, or one of the main components of this interstellar matter, is the gas. And gas is made of, could be atoms, could be molecules, could be both of them. And the atoms shown here are the hydrogen atom and oxygen atom, so the atomic structures of those is essentially the smallest unit of matter, of ordinary matter, right? They are neutral particles of specific chemical elements. And so they consist of nuclei made of protons in case of hydrogen atom, or protons and neutrons in case of other atoms, and electrons orbiting it at various distances in various orbitals. They all formed by nuclear fusion, which we call nucleosynthesis, either right after the Big Bang in the early universe, at least hydrogen, helium, and some fraction of lithium. And all the rest of the elements have been formed in stars. And you'll hear about it in the lecture by Hans Olofsson later, and the lecture by Barbara Ryden, which one is the next one. Then these atoms could be assembled into molecules, which is shown here on the left. This is the water molecule in its electronic structure. And the molecule is the smallest particle of a chemical compound that, you know, retains its chemical properties. You cannot split it more without losing that chemical similarity. Essentially, molecules are atoms that are bound together by sharing electrons that are in these outermost electronic shells. We call it chemical bonds, which is, in essence, a chemical bond. It's like a delicate balance between attractive and repulsive forces between the atoms. In addition to atoms and molecules, we have also ions in space. That's essentially charged atom or molecule, so it can be negatively charged. If it has an extra electron, could be positively charged if one or several electrons are removed from it, for example, by high energy ultraviolet photons. And we also sometimes in chemistry talking about radicals. That's essentially, well, it's a loose definition, but something that has unpaired electrons in the outermost shells that makes a specific compound very chemically reactive, such that even under very, very low temperatures in space, they can form new stuff. Well, in chemical reactions, it's a process, you know, it's a process that leads to transformation of one chemical species, set of chemical species to another. And it involves the changing position of electrons in the reactants and then forming products and sometimes breaking bonds and so on. But in principle, it's a transformation of chemical substances by creating, changing, or destruction of chemical bonds. In essence, it's, as I said, it's kind of rearrangement of out electrons called sometimes valence electrons. Schematically, it looks like that, for example, imagine two molecules or two atoms, A and B, that manage to come close to each other. And the electrons could start to interact, and they form what is called by chemists activated complex. That's, I mean, it's better shown here. You have the reaction coordinates like an abstract axis in the x-axis of the way how the reaction progresses. It has no physical meaning. On the y-axis, you have a potential energy, so the energy inside of the reactants, and then the activated complex that has an extra energy that needs to be applied to rearrange these chemical bonds. And then, if it is successful, then the products formed during this very short amount of time, they could get stabilized, and so by that way, one could create one or several products. And this specific, very simple potential energy curve shown here, as you can see, the potential energy of products is below the potential energy of the reactants. That means in the process of the reaction, the energy was released. And in this case, it would be the extra energy that would go to the kinetic energy of products, so they will fly away from each other. So besides atoms and molecules, we have dust in the interstellar space. And what is dust is kind of, it's a loosely defined topic. It's essentially what is solids, right, versus gas. But in principle, if you imagine chemical reactions forming bigger and bigger molecules, at some point they start become clusters. and they grow even bigger. At some point, they become what we call nanometer-sized particles, and that's kind of a loose definition when we could start calling them solids, because they have slightly different, they show different properties in the way how they interact with the light, and the electric properties start to change. And then, of course, these solids can stick to each other and create even bigger macroscopic particles. The size of them, let's say microscopic, it's 100 nanometers. So it's like 10 to the power of minus 5 centimeters. It's something you can see with your naked eye. It's called classical dust. And 1 nanometer, by the way, is 10 to the minus 9 of a meter, or 10 minus 7 centimeters. As I say, the size is starting from 1 nanometer, so about, let's say, 10 to minus 7 centimeters or so. They're bound together, you know, the constituents in the solids by covalent bonds, for example, in diamonds, or electrostatic van der Waals forces like in silicates, or high-density electronic clouds in metals, like in the iron. They're very efficient absorbers of light, unlike the molecules. I will talk about it later. Therefore, they determine the opaqueness of the interstellar matter. All right, let's go back to Eddington. What was his thoughts? Why he was skeptical about molecules in space? In his Bakerian lecture in 1926, he essentially said that it is difficult to admit the existence of molecules in interstellar space, because when once somehow a molecule ends up being there and gets dissociated, there seems to be no chance of the constituent atoms joining up again. So that was his argument against molecules being present in the interstellar space. Now we know it's not true, but of course he was true in the sense that the conditions in space are quite different from what we are used to on Earth, and they might not seem to be favorable for active chemistry and a lot of molecules being present in space. So how they differ? Like, imagine a unit volume of gas, like let's say 1 cubic centimeter on the sea level on Earth. It's schematically shown by this blue square. It would contain this cube about 10 to the 19 particles per cubic centimeter, mainly molecular nitrogen, molecular oxygen, some other gases, and so on, argon. If you go to interstellar space, the density is radically different. It's maybe 1 to 1,000 particles per cubic centimeters. So it's much more diffuse. Also, the temperatures are much colder on the sea level on Earth, depending where you are, but usually, let's say if you're in the tropics, it's maybe 20, 30 degrees centigrade. And by the way, in astrophysics, we use kelvins, which is the same as Celsius, but you have to add 273 to the Celsius to get this scale. So it's about 300 degrees Kelvin. But in the interstellar space, the typical temperatures are between 10 and 100 Kelvin. So they are cryogenic, as we call it, as we usually call it in physics. So they are below minus 150 degrees centigrade. It means because of these low temperatures, the reactions that have strong activation barriers, it means one has to one has to collide at high speeds in order to create new products. These reactions don't occur, and they're quite normal for atmospheric chemistry or the chemical reactions in our oceans. Also, because the ultra-high vacuum conditions, very low pressure, it's hard for the reactants to collide. So the time scale for collision is very long compared to what we used on Earth. And also in the atmosphere, we have a lot of three-body collisions when 3 particles could collide at the same time. It's not the case, or rarely the case, in the interstellar space. Despite that, there are tons of various gas phase molecular processes that are active in space, and Eric Herbst will give a lecture about it. I won't go into details here, and this is a small table with the name and the example. But in essence, you can form molecular bonds by radiative association and create molecules out of atoms. And then as soon as you have molecules, they can be ionized by high-energy UV radiation, creating electrons and the molecular ions, and molecular ions can react with neutral molecules by very fast, very efficient ion molecule reaction, creating other molecular ions. These molecular ions can meet an electron and get dissociated and create smaller neutral products. And of course, also the molecules can be also destroyed by interstellar UV radiation. And in addition to the chemical processes happening in the gas phase, there are also very active dust surface chemistry. If you remember, I mentioned that there is dust in the interstellar space. Dust serves two purposes. First of all, it provides surface for the stuff, for the atoms and molecules that are in the gas phase to stick to it, because the temperatures allow a lot of molecules do that, except of very lightweight molecular hydrogen that usually don't freeze out. And this is schematically shown here. This gray circle is the dust grain, usually it's silicate or carbonaceous stuff. And then the smaller circles are the individual atoms or molecules. It's hypothetical plot. Real grains are very porous, very non-spherical, very complex. And then this is how it happens. So you have accretion when the stuff sticks to the dust upon a collision. If the temperature of the grain right and the masses of these particles, this species is not very high, they can thermally diffuse over the surface, or if it's atomic hydrogen, it can tunnel through the potential wells of the surface sites to which these molecules stick to. Usually it's electrostatic van der Waals force, and some species can form chemical bonds with the surface, and then they are not movable. But then if they are still movable, they can find each other and form a new molecule. And this is how molecular hydrogen is formed in space, solely or almost solely by dust surface reactions, at least in the universe nowadays, not in the early universe. And water forms largely by this way. Ammonia, a lot of prebiotic organics forms in space via the surface recombination. And I think it will be Martin Makustra, probably also Alexei Potapov, and as well as Paulo Caselli and Ted Bergen will be talking, maybe Eric Herbst as well, about these processes. And then, of course, these freshly formed molecules sitting on the surface could either be destroyed by high energy radiation or could desorb back to the gas phase, either again by that upon absorbing high energy photon, or just because the temperature of the matter is increasing and all the ice is covering the particle, the dust particle, then they would evaporate. The information about these astrochemical processes are nowadays available publicly in various chemical reaction databases. They usually they list the reactants, then the products, then reaction rate constants, describing how fast reaction could be, its temperature dependence, energy barriers, and a lot of other stuff. There are two main ones. One is called UMIST, Database for Astrochemistry, UDFA. It's from the University of Manchester in UK. And another one is called KIDA, Kinetic Database for Astrochemistry, maintained by University of Bordeaux in France. They all contain about 7,000-8,000 reactions among more than 500 species, atoms and molecules and ions, made of 13 or up to 17 elements. And these are the links, you can look it up. About only 30 to 40% of reaction rate data in these databases have been accurately measured or calculated. And I don't have time to go into much details regarding the experiments. Martin Makustra, Alexei Potapov, Wolf Geppert, and some other lecturers will mention the techniques that I used to do that. But it's a difficult job, but it's very, very important, because otherwise we are not able to use this information to do the proper theoretical modeling and in order to explain what we are observing. In terms of modeling, the computational astrochemistry is essentially solving a system of ordinary differential equation, where on the left-hand side you have the net change of a specific species abundance I over time, And on the right-hand side, you have the sum over the terms in which this species is being formed, minus some of the reactions in which this species is destroyed. And here the species is I. And in order to solve this system of differential equations using the kinetic data from reaction databases, one has to kind of assume or know a priori physical conditions in the specific cosmic environments that we are modeling. Then, of course, one has to know something about the initial abundances of at least the elements in space, and then use appropriate chemical network extracted from a chemical database. We have a numerical solver in a specific programming language, Fortran, Python, whatever, and then have a good computer. And then you can get a theoretical abundance curve shown on the right hand side, where x-axis is logarithm of time in years, from 1 year to 100 million years, and y-axis is logarithm of abundance, relative abundance of the molecule CO, carbon monoxide, with respect to the total amount of gas particles per unit gas volume. And this is what you get as an output from the models. All right, so let's move on. Let's move on now. I briefly touched the key aspects, and then let's continue with the definitions, maybe to clear a bit your mind. What actually is the cosmic matter in our galaxy, which is called Milky Way? As I mentioned, it's mainly atoms and molecules and ions. It's just gas, we call it gas, and it's about 99 weight%. So it's 99% of the mass of this matter is in the gas particles. And it is shown here by this blue stuff. It's usually how the excited gas emission, molecular emission may look like. And then on the other hand, we have dust grains, which are submicron sized, tiny grains. It's only 1% or about 1% of the weight of the cosmic matter, interstellar matter. But they have much higher opaqueness, as I mentioned, and here they appear as this dark cloud that blocks the background radiation from the stars, from the excited gas. So they're absorbing this light, visual light, very efficiently, and then they emit it as the infrared or maybe submillimeter radiation. Well, in terms of the mass, this is for the Milky Way. The atomic hydrogen gas has a mass of about 5 times 10 to the 9 solar masses. And one solar mass, by the way, is about 2 times 10 to the 30 kilograms. Molecular gas, mostly made of H2, is about the same fraction, maybe a bit less. It's also 1 to 5, 10 to the 9 solar masses. The dust, as I say, the 1% of that mass. So it's 5 times 10 to the 7 solar masses. And in comparison, the stars, we have about 100 to 400 billion stars in the Milky Way. So their total masses between 4 and 6, 10 to the 10 solar masses. So it's like an order of magnitude above the gas mass. So the Milky Way is like 13 billion years old or about that. And it's already a relatively old galaxy. And it converted a lot of initial gas into stars over the lifetime. All right, what about what happens with this cosmic matter? What is the life cycle of it? This is very simplified picture, and Xander Tillens, Edwin Bergen, and Paolo Caselli and other lecturers will talk more about it, also Laura Kreidberg and so on. This is a very schematic plot about it. So we have large-scale diffuse gas, but it's not homogeneous. It is very clumpy and has on the much smaller scales because of the various physical processes like shock waves from the supernova or something. And this diffuse gas is in quasi-equilibrium, so it's not really collapsing. But if there is a supernova shock or something else, it could start fragmenting into smaller clumps, which could become so dense that the gravity would prevail over all other processes that can retard the contraction of the cloud. Let's say the thermal pressure, but temperature so low, it's not very high, or magnetic pressure, whatever, or turbulent pressure. And if the gravity prevails over these forces, this dense cloud would collapse. Because all clouds, they rotate slightly, and because of the conservation of angular momentum, this clouds collapses by a factor of several hundred. And in the process, it forms a very dense central region. It's first called protostar and then a star, when the nuclear reactions start in its center. And the remaining matter, because of the conservation of angular momentum, forms a tiny rotating disk-like object. We call it accretion disk or protoplanet disks. And the idea here is that centrifugal forces prevent the collapse in the direction perpendicular to the axis of rotation, but along the axis of rotation, the collapsing matter might move freely. And in the end, you have most of the initial or fraction of the initial gas mass locked in the central object in a star or binary stars, several stars. And then remaining few percent of the mass is in this disk. But this is very important phase because it is where the planets are forming later. So let me see. Yeah. And then at some point, the disk is dispersed when the planetary system is born. Then we have normal star and then planetary system, and then more primitive bodies like asteroids and comets. They could start falling into the planets, and they have very rich molecular composition and they could bring prebiotic organics into the surface of a the planet, the Earth-like planet that has a solid surface and in the habitable zone, the zone appropriate for the region of life, and you may form a life. And we are trying now to detect it in space, in other exoplanets by using very sensitive, expensive instruments. And then eventually the star will run out of the nuclear burning that actually what supports the collapse of a star. So essentially the nuclear burning creates the energy that counteracts the gravitational collapse of the star. But then eventually it runs out of the nuclear fusion, and then it either creates the white dwarf, and the outer shells are expelled by as winds, or if it is very massive, and this would be the destiny of the sun. But if it is more massive stars, then it explodes as the supernova violently. But anyway, the matter in the stars that now enriched by heavier elements formed in the core of the star by nuclear fusion, then they end up being again as a part of the gas in the interstellar matter, and this cycle starts again. So this is the cosmic life cycle of matter, very roughly. As I said, astronomy relies on observations of radiation. We cannot, most of the time, in the solar system, we can still fly to Mars and other planets, Venus, other planets, and measure chemical compositions and physical conditions in situ. But most of the objects we are interested in are much further away. We cannot fly there yet, and so we use the light to study their properties. And here I show you the Horsehead Nebula. This is dark, think closer to blue line in the Orion Nebula, the belt of Orion, which shows this. On the left-hand side, you see this blue bright dot. This is the very massive, very hot O-type star that emits a lot of the high-energy ultraviolet radiation. This radiation ionizes atomic hydrogen nearby, but this ionized atomic hydrogen collides with electrons and recombines back to the neutral form, and the excess of energy is emitted as photons of different energies. And this red glow is so-called H-alpha line. I think some reptilians will probably talk about it. It's what causes the red glows. It's in essence a combination of ionized hydrogen atoms that creates excited neutral hydrogen atoms that de-excite by emitting this specific radiation. And then there's, as you can see, there's this nebulosity with the blue stuff, and the white dot in the center. The white dot are the young stars, and the blue stuff is actually small dust grains that scatter away the stellar light. This is what you're looking at is the light scattered by the submicron-sized dust particles. And with telescopes, we can take the images of these things, and it's called imaging. And we can learn a lot of stuff about the objects that way. However, the most of the information about the chemical composition, also a lot about the physical conditions and kinematics, only comes from spectroscopy. And I will explain you what it is. In essence, it's essentially by looking not at the images, but looking at the spectra, by analyzing the emission or absorption lines of atoms or molecules. The beginning started with Newton, who had an amazing idea to use the prism and see what happens. And as you know, then you see the rainbow of colors. And what happens is that the light, the solar light get dispersed by the prism, and the photons of various energies, they kind of reflected inside the prism by different angles. And it creates this rainbow pattern where the red is the photons of low energy and the blue are the photons of high energy. And that he coined the term spectrum in this paper in Philosophical Transactions from 1675. And then people realized that if you put a slit in front of it and maybe the optical element or even a telescope, you could see interesting things. I mean, imagine, look at this plot. You see this hot light source like a lamp in the center. It's a very hot tungsten line that is shining, and it has a continuum spectrum. It's just essentially a black body at specific temperature, because it's a solid that is emitting. There are no any kind of spectral lines. And using this spectrometer with prism, you will see this continuous spectrum shown in the left top corner, where the intensity kind of varies smoothly with wavelengths, with the energy of the photon. On the right-hand side, in the upper part, you see the absorption line. When it is, if you imagine now, if you're on the right-hand side of the picture from the hot light source, and you have a cold gas cloud. This cold gas cloud will, the stuff there, the molecules, atoms, will absorb photons at specific wavelengths. These are the wavelengths, for example, for the atoms of the electron transitions between the individual electronic orbitals. And with the same instrument, with prism, you will see this as this dark lanes, like dark shades in the spectrum, and they appear in terms of intensity as these absorption lines. It's essentially the continuous spectrum of the background source that gets absorbed at very specific transitions or specific energies. And they're like fingerprints for the humans. They're unique for each element. And that's why we can identify them in a faraway objects. But we need, of course, the lab data, experimental data, to know which elements emit at what, have lines, absorption lines at what wavelengths. And then another situation, you can analyze this thin cloud of gas at different wavelengths, at a different angle, without a background source. And what you see then often is the emission from the cloud. So it's emission of the atoms or molecules in the cloud. By looking at what lines are visible, the emission lines, one could guess, for example, the temperature, the density of this. Besides what particles are shining, emitting this specific lines, one could even guess the physical conditions, because to get the lines in the emission, one has to have specific physical conditions like temperature and density. It started with the Joseph von Fraunhofer, German astronomer, who used this prism and detected absorption lines in the solar spectrum in the beginning of 19th century. And he referred in his paper that the lines and bands that are visible in the spectrum are not the artifacts. They are due to the nature of sunlight. And he had a drawing in the paper with very nice lines. They called Fraunhofer lines after him. And then actual real molecular spectroscopy has begun by two pioneers, actually from Heidelberg. It was the physicist Gustav Kirchhoff and the chemist Robert Bunsen, shown here. And we have a memorial plaque in the center of Heidelberg commemorating the way that they founded the spectral analysis of the remote objects like Sun and other stars in 1859. And the idea was that essentially Bunsen created very clean burner and was throwing different elements into the burner. And it was realized by the Kirchhoff that you look at the flame, that, for example, sodium would have a very specific, very bright emission line at very specific wavelengths. And he found out that it coincides very well with one of the brightest Fraunhofer lines that comes from the solar photosphere. And this line, of course, is an absorption because it's an outer photosphere. And the background radiation comes from the inner parts of the sun, and it's hotter. And they concluded that this line D, Fraunhofer line D in the solar spectrum, indicates the presence of sodium in the sun's atmosphere. It was the first time that composition of a remote object have been deducted by scientists. All right, so molecules. So in atoms, we have only electronic transitions. And they have an energy of several electron volts, which means in essence that the photons that are required to excite these transitions, or if the excited atom gets de-excited by emitting those, it's from ultraviolet to optical, infrared to optical. Ultraviolet to optical part of the spectrum. And molecules, and here what you see on the right hand side is on the y-axis is the potential energy of the molecule, and on the x-axis is the internuclear distance. And as you can see, the molecules have, it's an abstract curve, but the potential energy curves, there are two, one on the bottom that looks a bit like bell, skewed bell-like, and then another one above. So the bottom one is the ground electronic state of a molecule, and above bell curve, or skewed bell curve, is the excited electronic state. And electrons can also be excited in molecules and get de-excited. But in addition to that, because molecules have, they could be linear, could be so two-dimensional, could be three-dimensional. They can vibrate like that or like that. And so they have a lot of vibrational degrees of freedom, and then therefore they can also emit infrared vibrational lines. And usually the energy of those is the fraction of the electron volt up to 1 electron volt. These are the infrared part of the spectrum, not visible to the human eye, only to specific detectors. And then on top of that, the molecules also rotate around the center of the mass. And they have also rotational transitions, which are very, very low energy ones. There's a tiny fraction of electron volts. And therefore, they emit or they absorb in the radio part of the spectrum at sub-millimeter, millimeter wavelengths. And that's why molecules are so useful, and we like them so much in astronomy, because they have a lot of these transitions in different parts of the spectrum, and we can use them to learn a lot of stuff. For example, from the objects that are cold, so that electronic transitions wouldn't be excited, which is the case for the interstellar medium. The problem is that Earth's atmosphere is on the way. That's the problem for astronomers. As you can see on this schematic plot, on the y-axis, we have the atmospheric opacity from 0, completely transparent, to 100, completely opaque. And on the x-axis is the wavelengths. It's an energy of a photon from 0.1 nanometer, long radio wavelengths up, X-rays, gamma rays, all the way on the right-hand side to 1 kilometer wavelengths, which is like ultra low frequency radio. And you can see this blue dips is where the atmosphere is actually transparent. So we have this rainbow color showing that atmosphere is kind of transparent for the optical radiation, maybe a bit of the near infrared, but then maybe around 10 microns, but infrared part is kind of partly blocked, at least near infrared part. There are some windows, but it's already much harder to do the observations. But as soon as we go beyond 10 microns, it's completely blocked. And the same story is if you go beyond blue wavelengths in the spectrum, so towards the ultraviolet part and more energetic radiation like X-rays and gamma rays, it's completely opaque as well. So one has to put telescopes in the orbit, in satellites, to detect infrared radiation as well as high energy ultraviolet radiation and X-ray radiation. Hopefully, the part of the radio spectrum is accessible from the ground, which is very good, and we can observe stuff with radio telescopes. All right. So what are the molecules so what kind of molecules have been detected in space, and how and when? Initial detection came only in the almost middle of 20th century, like CH, CN, CH plus simple diatomic species have been detected right before the onset of the Second World War. Well, a little bit overlapping. They were been discovered as the absorption band in the optical light, when astronomers would observe some stars, and then the stuff is sitting along the line of sight in the interstellar space would absorb it. And then also even earlier, a lot of absorption lines of some other strange molecules or species that haven't been identified have been detected. It's about 500 of those. They're called diffuse interstellar bands. They're in the optics. They were discovered by Marie Heger already in 1922. Apparently, they're due to because of the large molecular carriers, for example, and they mostly remain. They're mostly unidentified to date, except of the C60 plus and a few other really huge molecules that people have managed to study in the laboratory and get the spectrum, and then realize, okay, that the line coincides with one of the diffuse interstellar band lines very well. That should be the carrier. But these are probably large polyaromatic hydrocarbons. I think Xander Tillins may talk more about that. But it's interesting that are still not very well known after more than 100 years of their discovery. Then the breakthrough came when the radio telescopes came to be after the Second World War, when the radar techniques have been really developed to very advanced stage. Atomic hydrogen line at 21 centimeter was first detected. That's the flip of the electron spin. So it's a very weird line. And then the hydroxide molecule, OH, was detected later in 1963 at 18 centimeter. And then ammonia was detected at 1 centimeter, and water as well in the late 60s. After that, because of the advancements of the rocket techniques, then it became possible to put telescopes in space, and Copernicus satellite in the 70s detected the electronic transitions of H2, as well as then later N2 molecules in space. And then later, radio telescopes operating at sub-millimeter, millimeter, centimeter regime, they started discovering the lines of rotational lines of other molecules like CO at 115 gigahertz, which is 3 millimeter, and then formaldehyde, H2CO, and so on. So this is the history of molecular detections in space. As you can see, we found almost 300 of them. And here the x-axis is year from 40s to 2020s, and the y-axis is cumulative number of detections. And as you can see that the pace has sped up in the last years. This is essentially because of the technological progress, because we have bigger and bigger telescopes and can detect weaker and weaker emission. And also the progress in laboratory studies allowed us to get more and more information about, the frequencies of the individual molecular lines from various molecules, so that we could identify them in space. This is the table showing the molecules as was last year. It shown here are 290 molecules ordered by the amount of atoms in them, from diatomic all the way to very huge molecules like on right bottom corner of C60 and C70. And as you can see, they range from simple ones like molecular hydrogen or carbon monoxide or molecular oxygen to more complex ones like water, which is important for life, or for example, for atomic ones like formaldehyde, which is important for the formation of sugars, or also a lot of nitriles, the molecules with CN group that are important for the formation of, amino acids and nuclear bases and so on and so forth. So and long carbon chains, of course. So it's amazing. So Arthur Eddington was very pessimistic in his assumption that there are no molecules in interstellar space. In fact, we know a lot of complex ones, and they are much more hidden there that we haven't found yet. Well, as I said, because of they have all these degrees of freedoms and all of these kinds of transitions, electronic, vibrational, rotational, molecules are very important because we can use them to probe the physical conditions, not actually chemical composition, but first and foremost, temperature, density of the gas, its ionization state, kinematics from the analysis of the line profiles. But also, of course, we are also kind of getting along the concentrations. And from that, knowing the temperature, density, and concentration of specific molecules, we could even assess their feedback on the environment, how important these specific molecules are for the heating and cooling of the gas, the underlying gas. And then, of course, from the chemical composition, we can also discern some information about what kind of chemical processes could form them. Are those that we have in the chemical databases enough to explain the presence of the specific molecules, or we're missing something, and so on? They have also specific role. They can be used as a kind of age indicator. So you can, in some rare cases, for some subset of objects, you can determine the ages. Is it a young object, let's say 1 million years old, or maybe it's already, this specific dense cloud or proton disks is already evolved, and it's maybe several million years old, or maybe 10 million years old, something like that. And of course, then we could, if we are talking about very complex organic-like molecules, we could start asking questions. What about prebiotic chemistry in space? What could it have been related to the origin of life? All right, I suggest we make a short break, let's say 5 minutes, because I'm a bit late, so that you guys could go outside, stretch, drink, and we will reconvene at in 7 minutes, let's say at 16:05 by Central European time. And I will be talking a little bit about, more about these other lectures and so on. Okay, so see you in 7 minutes. All right. I hope you spent this break time well, got hydrated and so on. Let's move on. I have other 30 slides to show. In the lecture by Barbara Ryden, she will be talking about the Big Bang, the origin of the universe. And what I mentioned, so this is because it's important for astrochemistry, is the formation of the elements and the formation of the molecules. You probably heard about Big Bang, that the universe has originated from apparently infinitely small singularity or kind of point in space that kind of exploded or violently expanded, and it was infinitely hot and extremely dense. But as it was expanding, it was cooling off, that allowed quark-gluon plasma to recombine and form baryonic matter. And then it continued an expansion, cooling off even further. That allowed from initially formed protons, neutrons to form more heavier nuclei. So this process it's called Big Bang nucleosynthesis. It was operating 10 seconds to 20 minutes after the Big Bang. And here you see not the chemical reactions, but nuclear reactions. But schematically they look similar, but of course the forces involved are not electrostatic forces, but strong and weak nuclear forces, electromagnetic forces. So it's different types of interactions. But in principle, within this 10 seconds to 20 minutes, these conditions were favorable. So it was not too hot and still dense enough for protons and neutrons to recombine and form deuterium atoms. And then deuterium atoms, they collided with protons and neutrons and formed either a lightweight isotope of helium-3, or heaviest isotope of hydrogen, tritium, hydrogen-3. And of course, deuteriums were also reacting with each other, forming helium-4, or lightweight version of helium-3, or maybe tritium, and so on, plus various products. And this helium-3 then was reacting with protons, neutrons, and deuterium atoms to form helium-4. This is a stable isotope of helium, otherwise called also alpha particle. It is without electrons. And then these elements have also been used to produce a little bit of lithium-7. But then the problem was that, I mean, one could imagine why that the processes would go further, would run further, so you could form more and more heavier elements, let's say carbon, oxygen, nitrogen, iron, and so on and so forth. However, there are no stable isotopes of element with atomic number 5 and 8, so essentially lithium-5 and beryllium-8. The reactions forming those those elements created during the Big Bang would decay backwards almost immediately. And that's why during the Big Bang nucleosynthesis, mainly hydrogen and helium and a bit of lithium-7 plus deuterium have been formed. By the rest of the stuff, the rest of the heavy elements have been formed inside the stars by the stellar nucleosynthesis. And actually our bodies, we have a lot of iron complexes and proteins and a lot of other stuff, calcium in the bones and so on. All these elements have been forged in stars. As Carl Sagan said, we are star stuff. And actually one of the main reaction that produced heavy elements was this so-called triple alpha process, when under very high densities of pressures and extreme temperatures, the 3 alpha particles via 3-body process would be forged into carbon atom. And actually, the first molecules appeared already after the redshift of about 1,000. And this is the very specific. First, I would like to show what redshift is. In essence, redshift is something that we use to measure the distances or maybe age of the object or age of the universe we are looking at. It is a Doppler shift between the line of element we know in the spectrum of a distant object versus the frequency of the wavelengths of the same element that we measure in the lab, divided by the frequency of wavelengths of the measured in the lab. So in essence, it shows how far away the emitted energy of specific line in the far distant object appear with respect to the lab standard. And redshift of about 1,000 corresponds to the early age of the universe. It's about 380,000 years. And this is the time when the universe has expanded so much that electrons could start recombine with protons and form neutral hydrogen atoms. And hydrogen, by the way, was and is the most abundant element that has been formed, with helium that is by weight maybe about 25%, and the rest is tiny. And we understand, by the way, these abundances of hydrogen, helium, and so on, and lithium-7 and deuterium by nowadays cosmological models simulating the early universe, the Big Bang, and the Big Bang nucleosynthesis quite well. So these models are correct. But then, as soon as we got neutral matter, so neutral hydrogen atoms, we could start forming molecular hydrogen. But even before that, there were some molecules. And most of these reactions have been ion molecule reactions. And all of these simple molecules have been constantly killed by very strong background radiation from the hot universe of the time. It cooled off a bit, but still, it was much hotter than today's. And the first molecule was a strange one, was helium H+. This molecular ion you cannot create in the lab because helium, as you know, it's noble gas, is not very reactive. It has completely filled outer electron shell. But in the early universe, in these conditions, this helium H+ was the first molecule that had been formed because helium has very high ionization potential. It recombined, become neutral during the expansion of the universe, before the hydrogen could become mostly neutral. And it formed via the radiation association between helium and H+. And there was another molecule, helium-2+, but it's more exotic. And then at some point when the universe has expanded even further, when as I said, hydrogen became mostly neutral, and it was the time when electrons became bound to hydrogens, and all of a sudden the universe had become completely neutral, or almost completely neutral, and the radiation that was coupled to it via the interactions with electron, the Thompson scattering, became decoupled from the matter. And this is last moment when the matter and the radiation had been coupled. We can observe nowadays at 7 centimeters. It's called cosmic microwave background radiation. At the time of the decoupling, this radiation was of the energy of 13.6 electron volts. So it's like ultraviolet radiation, but it decoupled because of the expansion. Its energy dropped to very low energies in the radio wavelengths part. But what about heavier elements? Initially, it wasn't clear how these other heavier elements after lithium could have been formed. And but by analyzing the solar abundances of the elements shown on this plot, on the y-axis, we have in logarithm units abundance of various elements with a very strange normalization when the abundance of silicon is assumed to be 10 to the 6. Don't ask me why, it's historical reasons. And on the x-axis, we have the atomic number, so the amount of protons in the nucleus of the elements. And as you can see, it in general, it decreases with the atomic number. So the heavier elements are less abundant. But also it has this very strange drop at lithium and beryllium. This is exactly what I said. It's because the elements around beryllium and lithium are not stable isotopologues, and beryllium, for example, nowadays universe is formed from heavier elements by the interaction with high energy cosmic rays. But then you have the peak at the carbon, because carbon can be forged inside massive stars. And then the rest of the elements from carbon and oxygen and nitrogen, they could be formed quite easily by adding either protons and neutrons or alpha particles to them. And this explains this even odd sawtooth-like pattern. And there's also actually a local peak in the abundance for the iron, but I won't spoil the lecture by Barbara, so you will learn about it. And also in the lecture of Hans Olofsson, of course. The stars, I mean, we now understand how the structure of the stars look like. It's a very schematic plot here, mainly showing my main point here for you is to show that they have very dense, very hot interior, or how we call it, core, where the nuclear fusion happens. Usually the temperature needs to be about 1 million Kelvin, preferably more, for the nuclear fusion to start, because in order to bring together two elements with the two nuclei with the positively charged, of course, protons, one has to overcome the Coulomb repulsion, which is very strong when you try to bring them close to each other. And the densities of the excess of, let's say, 150 grams per cubic centimeter, so it's much denser than the water, which is only, what, 1 gram per cubic centimeter, and the typical stones on Earth is about 2.5 to 3 grams per cubic centimeter. But the outer shells, the outer layers, which we see, like the outer rim of the sun disk, which we call the photosphere, the sphere, the place where the photons escape. They have temperatures only a few thousand to several tens of thousand Kelvin, and the density is much lower, 10⁻⁶ grams per cubic centimeter. They have enormous gradients of physical conditions from the center to the outer part. There are different processes that are happening in the stars. For the sun, it's too busy a plot. Please don't try to figure out what's going on. I don't really have time explaining it, but it's called hydrogen burning or proton-proton cycle. There are different versions of it, but in essence, what you have to remember, it starts at about 4 million Kelvin, which is kind of what we have in inside the sun's core. In the net effect is that the four protons are fused together to form helium-4 nucleus. So it's 2 protons, 2 neutrons bound for helium nucleus. And this is an energetically favorable process. Upon, of course, there is a barrier because of this Coulomb repulsion and so on. But then as soon as it's overcome, if the temperatures are high enough, the reactions, this nuclear fusion reactions, they produce energies. And this is the engine. It's the engine of the sun. This is it keeps it burning, and it creates and this energy escapes slowly the core in the form of photons that we can then see with our own eyes. As I said, in more massive stars, what could happen is that if they're very hot and very dense, that the three-body collisions with specific very quick intensity or quick pace could occur. One could fuse 3 helium nuclei, 3 alpha particles into one 12-carbon nucleus. That's the so-called triple alpha process of helium burning. It only occurs in stars more massive than the sun, and it requires temperatures of the excess of 100 million Kelvin. And it's an interesting process that we will learn about. the lecture of Hans Olofsson. Actually, while it looks pretty theoretical, what I've been showing you, we do have a direct image of the sun's core, the place where the nuclear fusion reactions in sun happens. Because during these reactions, one of the products are the neutrinos. These are the subatomic, almost massless particles that barely interact with matter. Therefore, they can, unlike photons, they can freely escape the core where they're born, going through the sun without any interaction. But they do still interact with matter from time to time. And the specific experiments that have been established here on Earth and mostly in the underground mines, like Supercameacanda, where you can detect the direction from where neutrino comes and intensity. And you can create the artificial photograph of the sun's core as shown here. This artificial color showing the intensity of the neutrino flux as over the entire sky. And what you can see this in the center, this green and the red blob, it's actually where the neutrino flux peaks, and it coincides with the sun. So we can look with neutrinos inside the sun. Okay, going from the sun and stellar nucleosynthesis and the Big Bang and Big Bang nucleosynthesis and the early universe, let's come back to the galaxy, to Milky Way. I mean, if you've seen the Milky Way with your own eye, you need to be in a dark place, which is hard to find nowadays, but it may look like that. So you see this glow in the sky, this whitish color. It's a black and white photo, by the way. These are the diffuse light of these 100 to 400 billion stars that you can't resolve because they're far away. And then these dark patches, which are kind of fractal, are the dust clouds that are absorbing this background light. These dust particles, as I say, they're mainly silicates and the carbonaceous. On the other hand, if you look into and by the way, I forgot to say that the Milky Way is a spiral galaxy, but the sun is like in the central plane of the spiral galaxy, and we see it like from inside, and it appears as this in the projection as just the lane of the sky. But if you go to radio wavelengths to 3 millimeters, where we can image the same sky and CO1 to 0 emission line. So this is the gas line that arises in the molecular gas, and this is how this Milky Way looks now, as you can see. In the center, there's galactic center where the supermassive black hole is, but you also see this that CO emission is patchy, and there are these strange names: Taurus Auriga, Perseus, Rho, Ophiuchus, Orion. These are essentially the names of various big heaps of gas and dust clouds intermixed with young stars. We call star formation regions, star-forming regions, or sometimes giant molecular clouds in the earlier phases. And these are the clouds made of partly molecular gas, or well, not largely molecular gas. The hydrogen exists already in molecular form, but usually there are not much more other molecules present. They have enormous masses, 10 to the 4, 10 to the 7 solar masses, which is like 2 times 10 to the 34 to 37 kilograms. They have sizes from 10 to 200 parsecs, which is about like 3 times 10 to the 14 to 6 times 10 to 15 kilometers. And they are very fractal, so they have this large-scale diffuse component, like diffuse interstellar matter. It's a temperature of about 100 Kelvin or about minus 170 Celsius, and the particle density of 100 particles per cubic centimeter roughly. And some of this, embedded within this large-scale diffuse gas component, there are like much smaller, much denser individual dense clouds. They're of the fraction of a parsec, so it's about, let's say, 3 times 10 to the 12 kilometers, which is about 100 to 200 times bigger than the size of the solar system. the temperatures in them are much lower, 10 to 20 Kelvin, because they are denser. Their densities are 10,000 or even more particles per cubic centimeters. And the dust that is sitting inside this is the gas and these dust clouds. Because of this high density concentration, it makes the cloud completely opaque to the optical radiation, and that also means that because dust is efficient absorber of visual or optical or whatever, the light, in essence, especially in the ultraviolet optical range, then and it can re-emit it very efficiently. It also cools off these clouds very efficiently. And this is the seeds where later the stars and planetary systems would form. Actually, surprisingly, inside this diffuse gas, you have very, very, very interesting chemistry starting from molecular hydrogen. It can get ionized, creating H2 plus molecular ion. So if you're looking at this inverted Christmas tree in astrochemistry, you can see that H2 then goes to H2 plus, then H2 plus reacts with another molecular hydrogen, forming He plus molecular ion. And this is very efficiently reacting with elements like atomic carbon, atomic oxygen, deuterium, forming multitude of very interesting molecular ions that can get neutralized by short recombination with electrons and form neutral smaller molecules or atoms. Wolf Geppert, I think, and Eric Herbst, as well as Paulo Caselli, probably Ted Bergen, will be talking to some extent about this stuff. In addition to that, in these dense clouds, which are cold, where a lot of molecules can collide in the centers with the dust grains and stick to it, there are a lot of processes forming complex molecules. Here I show you how the CO that is on the top of this round diagram, CO molecule that got stuck on the surface of such a grain could get hydrogenated by, essentially, it can react with atomic hydrogen to form HCO, and then HCO can react with another atomic hydrogen, form formaldehyde molecule, H2CO, which then, through two other reactions, different pathways also involving atomic hydrogen, could form hydroxymethyl and methoxy radical, which then as well react with yet another atomic hydrogen to form simplest alcohol, methanol. And then radicals, HCO radical itself, can react with each other and form aldehydes, the precursors of sugars, as I say it. And this kind of chemistry also operates for other compounds like hydrocarbons, to some extent also nitrogen. And a lot of these processes are being studied in the lab. And I think Martin Makustra, Alexei Potapov, probably Paulo Caselli from Observational side will be talking about that. Anyway, we also have a lot of instrumentation that we use to study this kind of very exciting environments, both from the ground but also from space. And I think it will be Rance Waters who will be talking about instrumentation, but you will hear about these instruments later in the lecture. Well, in the far infrared part of spectrum, for which the atmosphere, Earth's atmosphere, is completely not transparent, we had Herschel Space Observatory operating 2009-2013, named after the German brother and sister Herschel. And for example, there were a lot of data taken with that, but I'd like to show you just this beautiful photo in false colors showing the distribution of gas in a star formation complex called Cygnus X. It's in the constellation of Cygnus, where you see very fractal gas patches and then some kind of bright spots where the young stars are, which ionized and excite gas emission, and also dark patches where the dust are and there are no stars, yes, and some reddish colored points is where the freshly formed star or not yet formed star is still enshrouded in the gas and dust cloud, blocking its light, making this light appear red. Herschel also detected molecular oxygen in interstellar space. So molecular oxygen exists not only in our atmosphere, where it is produced by mainly photosynthesis, by mostly the planktons in the ocean, but also in the interstellar space it exists, which is very cool. And then, of course, we can observe individual denser clumps, which later would form a star plus planetary system around it. And on the left top panel, you see such an example dense cloud called Barnard 68. What you see is this black hole, so to say. It's not a black hole; it's a kind of essentially the silhouette of this dense cloud. That essentially is the small dust grains sitting in the cloud, blocking the light from background stellar stars, and therefore it appears as this black hole, so to say. On the right-hand side and also on the bottom row, you see the emission of various molecules, and 2H plus on the right-hand top part, then CS on the right-hand bottom part, and then rare isotope lock of CO, C18 on the left-hand bottom part. And as you can see, these molecules, they shine from various parts of these clouds. So in that sense, since these objects are nearby, with modern telescopes, we can study the special distribution of molecules there and what it might mean in terms of chemistry. Of course, besides imaging, as I said, spectroscopy is very important. And here is the Herschel, the spectrum taken at mid-infrared, close to kind of far infrared part of Orion Nebula, or towards one of the Orion Nebula components. So it's a massive gas cloud that's warm. There's a lot of complex molecules that are formed via surface chemistry being evaporated, and that are in the gas phase. And I don't know if you can read it, but there are first of all, you see this forest of lines, this individual lines, emission lines of various molecules, and we have interesting ones like methanol, simplest alcohol, then hydrogen cyanide, HCN, precursor of amino acids and nuclear bases. Then we have sulfur dioxide, then dimethyl ether and water and carbon monoxide, and so on and so forth. We have detected, as I said, also beside methanol, we also detected ethanol, so the real alcohol in space, as well as sugars like glycolaldehyde. This is the observations made at sub-millimeter wavelengths with Atacama Large Millimeter Array in San Pedro de Atacama Desert in Chile. So it's a radio telescope, radio observatory. And there were some funny, newspaper articles about, like how much alcohol it is there and how long it will take for humanity to drink it up if everyone consumes 1 liter of alcohol per day. It was like several tens of thousands of years. Anyway, and then in interesting environments, out of which on the way of, that appear during the the formation of a star is called protoplanetary disks. These are the places where the planets form. It's as I said, it's a remnant material that orbits around the freshly formed star. A solar system has passed the same stage, and it's very important stage because the conditions in these protoplanetary disks, they determine what kind of planets you may get around the star. And Catherine Walsh, as well as to some extent Sean Raymond and Alessandro Morbidelli, will be talking about these disks and the solar nebula and the formation of the solar system. We now can image these planet-forming systems very easily at radio wavelengths, for example, with Atacama Large Millimeter Array, which is shown on the bottom and the left-hand top sub-panel. You see this ring-like symmetric plot of a millimeter dust emitting in the planet-forming disk around star HL Tau. It's as well false color, just indicating the intensity of the radiation. It's at, I think it's sub-millimeter, it's like 0.8 millimeter or so you can see it with the naked eye. But you can see these concentric dark rings. This what we think. How the planet formation may look like. If there are like big planet embryos or maybe already planets, while the disk gas and dust are still around, these planets may kind of carve the material-free rings around the orbital path, and maybe that's what we are looking at. The innermost ring, by the way, on this image is of the distance of Saturn from the Sun, so it's exciting. And there are much more disks that show the same kind of pattern of being circularly symmetrical, appearing like the circles or ellipses, but also having this concentric azimutally symmetric rings and gaps. So we believe that that's probably we could be witnessing the formation of planets there, but we are not 100% sure yet. The same disks can be imaged in the molecular emission lines from various molecules. There have been such a study, very interesting one. And what I show here, 5 rows of various molecular emission indicated on the x-axis. So you have to turn your head like that to read the specific rotational line. But as you can see, these are like emission from CO, monoxide, and its isotopologues like hydrocarbons like C2H, then nitrides like CN, HCN, CH3CN, formaldehyde, H2CO, and then also nitriles like HC3N, cyanacetylene, and so on. As you can see, there are also kind of organic species that are already present there, even maybe before the planets are fully assembled yet. So that raises the question whether they could have been important for the origin of life, let's say in our own solar system, or maybe in other planets. Alexei Potapov and maybe Dieter Braun will talk about it in more details. And actually, we have found, we caught such a young planet in a young system where the star has formed and the gas and the dust of a disk is still present there. It is shown here, like on the left-hand side panel. You see a bretzel-like structure. This is the emission of the or scattering of the dust grain. The star is in the center, but the stellar light is blocked by the coronographic mask in the Very Large Telescope with the sphere instrument. And this this very bright dot is actually the emission from the planet. And actually on the right-hand side, it's another image of the same system taken with another instrument at VLT called MUSE, where there are 2 blobs. Actually, there are 2 planets, and I've heard from James Webb Space Telescope observations, they have found the 3rd one. And this is a very young system. The Sun-like star has an age of 5 million years old. It still has a disk around it. And these 2 gas giant planets with the masses 2 to 10 Jupiter masses, they're at 20 and 36 astronomical units. So 22 and 36 times the distance between Earth and the Sun. Interestingly, in the mean motion resonance, the orbits are dynamically coupled. And they still accreting gas, so they're still slow, maybe a little bit growing. And then, of course, with James Webb Space Telescope that has been recently launched, it operates between 0.6 and 28 microns in a near-infrared, mid-infrared wavelength range. You have to do it from the outside of the atmosphere. They even detected water vapor emitting from the innermost region of this disk around PDA-70, where these 2 giant planets are, meaning that if terrestrial rocky planets like Earth are forming there, they would have water and maybe could become habitable later. There will be, of course, the lecture. Now, sorry, I have to speed up in order to be able to answer your questions. There will be the lectures by Alexandra Morbidelli and Sean Raymond about the solar system and the formation of the solar system. You will learn what the planet is, but roughly, the planet is something that is massive enough to be round, but not massive enough to start nuclear fusion, and massive enough to clear the orbital path around it. And in the solar system, we have rocky planets or terrestrial planets that have the mass of the atmosphere is much smaller than the mass of this solid, core and the mantle. These are Mercury, Venus, Earth, and Mars. And then, of course, we have gas giants, Jupiter, Saturn, Uranus, and Neptune. So they have extensive gaseous envelopes. And Pluto, that was called planet in the beginning, was denominated because it lacks mass to clear the orbital path around it. So it's a dwarf planet and not planet around them. And then you learn what we can learn about, the composition of the atmospheres via spectroscopy from the Earth, as well as from the space missions like Cassini mission to Saturn or Rosetta mission to the comet 67P, and the missions to asteroids like Hayabusa 2 and Osiris-Rex and so on and so forth. I have no time, fortunately, to mention that. And then in the lecture by Laura Kreidberg, you will learn about exoplanets. And what we learned so far is almost every star in the Milky Way has a planet around it, at least one. And that we call them differently in astronomy. We called, mostly solid-like planet without massive atmospheres, Earth and super Earth-like. They may have the radius up to 2 Earth radii, but anything bigger should already have a prominent gaseous envelope. And depending how large it is, we call it Neptune, mini Neptune, or large Neptune, or if it's more than 6 Earth radii, then it's already gas giant like Saturn and Jupiter. In this diagram showing on the x-axis the orbital period and the y-axis the planet mass, with all these multicolored dots, is what we're looking at as are the all or almost all exoplanets discovered today, at least until 2020 or so. It's a bit more. I think nowadays it's about 5,800 discovered. And as you can see, I mean, the yellow or rather like yellow-orange color shows Jupiter, Saturn, Neptune, so the solar system planets, Earth, Venus, and Mars. As you can see, I mean, we haven't detected many Earth-like planets because they're tiny, it's hard to detect, but we detected tons of gas giants and Neptune-like planets, a bit of the super Earth, so like rocky-like planets, which are slightly more massive than the Earth, like a factor of 2, 3 or so. And this is an example like how some of these gas giants have been discovered. There is the system called AHR 8799. It has at least 4 gas giant planets somehow from very large distances from the star, like factor of several hundred to several thousand times the distance between the sun and the Earth. And they've been discovered almost 15 years ago, and they've been constantly observed, and now we can see how these planets move around their central star in real life. So you can see these 4 blobs that slowly moves. Of course, the innermost one orbits faster than the outermost ones because of the Keplerian rotation law. So, and then we're finding more and more of the system. But of course, the majority of the exoplanets have been found indirectly, for example, by the transit method, when the orientation of the planet orbit is favorable in such a way that it passes in front of its central star, and we can see it like that, and it looks like a dip in the lightness of the star with a certain duration. And by analysis of this dip, we can determine the radius of the planet, and by knowing the orbital period, because these dips, they would repeat, right? Periodically, we could discern the radius of the orbit and therefore the mass, knowing the mass of the star. And so we can discern a lot, like mean density. But interestingly, if you do the spectroscopy of this transit, the magnitude at which the intensity drops would appear differently at different wavelengths. And it might tell you about how the light gets transported through the upper atmosphere. In that way, we can study the physical condition and chemistry of the upper atmospheres. And by that method, for example, Hubble Space Telescope have discovered water vapor in the atmosphere of the super Earth K2-18b. It's 8 times more massive planet. That between super Earth and mini Neptune, so it has enough mass and relatively massive atmosphere, but not supermassive. And on the left-hand panel, we see how this transit that looks like a bit like the cup-like form looks like at different near-infrared wavelengths. And on the right-hand side, you see this black lines with the dots. These are the measurements, and the multicolored lines are different atmospheric models. And the conclusion was the model with the clouds might not be the best, or maybe the best, depending how interpreted. But nowadays we can even get the atmospheric composition, the presence or absence of the clouds and such. Some of the exoplanets. James Webb, so more recent, more powerful telescope operating near mid-infrared wavelengths, also analyzed the spectrum of this planet. And as you can see, the measurements from James Webb are these white dots with the vertical white lines. But then you see this blue complex wave-like spectrum. This is the best fit model. But as you can see, what have been found is the emission of carbon dioxide, the presence of methane as well, maybe even dimethyl sulfide, a molecule that on Earth only produced by life. And it's hard to produce it by inorganically. But it's not clear if this detection or it's a false signal. We have to look further. And then also James Webb, for example, recently imaged the atmospheric spectrum of another transiting planet, which is super Neptune, which is hot. It's close to its star with a temperature of about 500 degrees Celsius. It's called WASP 107b. And there you can also see the measurements as this white stars, and the best fit model is this orange line, and you can see the presence of sulfur dioxide, emission lines of water, maybe silicate clouds, and so on. Okay.
20 minutes.
Yes. It's the last slide of my lecture. So I'm ready for your questions. I hope you enjoy it and it wasn't too complicated. So thanks a lot for your attention. So how do we do it?
Okay, thank you, Dima, very much for your presentation. And now the lecture is open for questions. So please raise your hand or ask your questions in the chat. Dima, you could probably already look in the chat.
Yes.
Already some questions there.
I mean, because there's so many comments, I don't see it.
Yes, there was a comment from Alejandro Garcia.
Mm-hmm.
So maybe
Alejandro Garcia. Is it about okay, that was during the lecture about the reactions. Maybe if you could ask it again. Okay. Yeah. Well, let me first answer the questions that in the end of the chat. Sorry for those who already asked, but for me it's easier. It's about what if the specific line of a molecule coincides with another one. This is really an issue, especially for complex organic molecules, which have such a high degree of freedoms that have multiple lines, which are very weak because emitted energy is distributed over many lines, so each line is very weak. And often enough, you cannot claim the detection of exciting prebiotic organic molecule in space if you only identified one line, because it could be a line from something else. Yeah, this is confusion that is annoying. One has to know, preferably by having high quality lab spectrum of a specific molecule or molecular ion to look for other transitions and confirm its presence. New elements in space. So it's a good question. I don't think it's really the case. We analyzed the solar photosphere and also primitive meteorites quite well, and because these things are nearby meteorites, we can find on Earth with very powerful, very sensitive chemical analytical techniques. We know the abundances of very rare elements as well as isotope logs quite well. There may be some that we are missing that may be somewhere else or at larger distances in the universe, but we don't have sensitivity maybe to find it. But it's a good question, actually. I mean, in terms of the useful distance in obtaining, like finding new molecule, there are several regions that are being used to find, for example, new exciting prebiotic organic molecules or just organic molecules. there is a massive gas cloud around the center of our galaxy. It's called Sagittarius B cloud. It's warm enough and it's dense enough so that the chemistry is very efficient both in the gas phase and the surface of dust grains, so it's not too hot. Yet it's warm enough that a lot of these complex organic molecules can be dissolved to the gas phase, and there we are finding a lot of stuff. Also in the massive star-forming regions in Orion, which is much closer to us, but is not as maybe massive as this Sagittarius B2 cloud, then we also could find a lot of complex organic stuff. Yeah, in terms of the conservation of the charge, yeah. I mean, I could have forgotten to put the electrons. You're right. It should be conserved. Of course, you have the conservation laws operating both for the molecular reactions, but also for the nuclear reactions. No, Alejandro, you're right. I could have made a mistake for sure. Neutrinos, yeah. So neutrinos, I think they don't interact
Dima,
with...
sorry, could
Yes.
you please read the
Yeah,
question so everybody understands?
Yeah, sorry, exactly. I'm sorry, I apologize. There was a question about whether neutrinos interact the same way as like protons and neutrons. I think they interact. They don't really interact well with the electromagnetic radiation like protons and neutrons. But they do interact with the particles, so they can collide with the particles and break it a piece. So therefore, we are not detecting directly the neutrinos, but the products of the interaction with other nuclei. And so, yeah, the neutrinos do have masses, just very tiny ones. Please repeat the title of the book of Eddington. Oh, it's not a book. It's a Bakerian lecture. It's a prestigious lecture that I think it's held each year, or I think it's still being held by renowned physicists in UK. I forgot if it is in Oxford or somewhere else. Each year it is someone else. You can look it up in the Wikipedia. I'm not sure you can find it online, but who knows? Probably they can find it. What happens when dust reacts with stars? I mean, dust is formed actually in the expanding shells of dying stars, but in principle, the conditions, even in the photospheres, the temperatures are so high that most of the stars, or many stars, that solids cannot survive. Even molecules have difficulty to survive, and there are no solids. There is an excellent question that the first molecule H2 was formed in the early universe solely via gas phase reactions. And the beginning of the universe, of course, there was no dust. So how the formation happened? This is an excellent question. In fact, as I said, nowadays, so in the interstellar matter around us, it solely or almost solely happens via dust surface recombination, because it's just more efficient process. And the reason for that hydrogen has a problem of getting rid of excess of energy when two hydrogen atoms colliding, forming this activated complex. So it cannot get stabilized. But if it happens on the dust grain surface, then dust lattice absorbs the excess of energy and hydrogen molecule can be formed very efficiently. In the early universe, there were no heavy elements, therefore there were no dust. Therefore, there were these circumstantial gas reactions involving ionized helium and neutral helium. And they were happening because the universe was much smaller, much denser. Even in that case, the abundances of this molecular hydrogen in the universe were tiny with respect to abundances of atomic hydrogen or ionized atomic hydrogen. Well, I mean, yeah, there was a question if HO2 plus ion was detected recently. This, I don't know, I might have missed it, maybe. The question is why the ion molecule reactions are most important. It's another excellent question. And the reason for that is that imagine a vast interstellar space where there is very little stuff flying around. And imagine you have two neutral molecules or radicals or imagine radicals. They're ready to react with each other, but they need to collide with each other to react to form something else. And now imagine you have a molecule on the one hand, neutral molecule, and an ionized atom or ionized molecule. Many molecules, they are polarizable, which means they have dipole moment, which essentially means that the central of mass and the central of charge does not coincide, and usually often the case. And then if such a molecule would approach a charged species, then the electron cloud would feel the presence of the positive charge from the positively charged ion, and there will be a Coulomb force induced between the two, and there will be a large scale attraction force. For example, let's say they would fly like that, but because of this Coulomb attraction, they would collide with each other, and the probability of ion molecule reactions therefore is much higher in the interstellar medium. And in the Earth's atmosphere, we don't have, hopefully, high ionizing radiation nearby. Therefore, it's not reactions. Yeah, and ion molecule reactions obviously have been very important in the early universe because the background radiation was much stronger. The question about on the last several slides whether atmospheric spectra of the exoplanets have been shown. Why the spectral lines of molecules broaden so much? It's an excellent question because it depends. The broadening of these lines, I had no time to talk about it, unfortunately, but the width of the lines and their shape reflects the physical condition of the gas. It's either rotation or kind of dynamical processes that can broaden the line, as well as pressure, which means temperature. And of course, for the super Neptune, it has a temperature of 800 degrees Kelvin or so, about 500 degrees centigrade. Plus the densities are high. So the spectrum that have been measured with James Webb in this one got broadened because essentially the temperature as well as maybe dynamics of the atmosphere, they broadened the lines of the molecules. In the lab, if you would do the same experiment, but at the less dense conditions and less cooler, then the line would be much narrower. That's the explanation. That's another question I liked someone asked is about I mentioned that the accuracy of the astrochemical models depend on the accuracy of the chemical data that are assembled in this public astrochemical databases. And I showed to you that about maybe 30 to 40% of reaction rates in these databases are accurately determined and the rest are not. The question was how it affects the uncertainties of the models. It is very, very good question. There have been studies like that. Ballpark estimate is that diatomic, triatomic molecules, which we know very well and can measure in the lab or study in the lab very efficiently, like carbon monoxide, water, I don't know, ammonia, whatever, formaldehyde. We can predict their abundance, and the reaction rates have been measured very accurately. Then we can predict the abundances within that uncertainty of, let's say, I don't know, 20%, 50%, which is for astronomy is good enough, you know. But any kind of complex organic molecule, methanol, ethanol, glycolaldehyde, you know, involving 6 atoms or 8 atoms or something like that, often enough, uncertainties are so large that we can predict the abundances only by, let's say, an order of magnitude, maybe even 2 orders of magnitude. Yeah, so it is complicated sometimes. There is a question about the difference between the reaction index ISM and on the ISM. I think it's, maybe I misspoke. It's what I was talking about, the interstellar medium ISM, and reactions are happening in this interstellar medium. Let me see what else. About the master projects, it's hard to say, you know, there are a lot of stuff to do. Sometimes it's complex, but one has to see, you know, there are often enough, you know, a lot of the projects, master projects related to astrochemistry are involving observational data, because it's the easiest thing you can do in astrochemistry is to get another spectrum of an object. And it's, in my experience, much harder to then use a model and try explaining it. Or let's say you go to the laboratory and try explaining what happens inside the laboratory experiment. And you can expect a lot of the master projects in astrochemistry would involve dealing with radio observations or infrared observations of various molecules in different objects. I don't know, planet-forming disks, molecular clouds, or whatever. What are other locations where the molecules can be found apart from the interstellar meta-engineer? This is a very good question. We found them everywhere. I forgot to mention that, by the way. I had a slide, but had to cut it out. Now we're detecting them in high redshift quasars, essentially very early galaxies, at the time when the universe was maybe only several 100 million years old. We're finding them we found them in the solar photosphere and atmospheres of planets in the solar system, also in the moons like Titan. Of course, we found them in comets and asteroids. We found them in other exoplanets. Now we are trying to find exocomets. So they're essentially everywhere in space to some extent, even in intergalactic medium. This actually, I don't know. Intergalactic medium is too dilute and too heavily ionized. I think there are no molecules detected so far as I know. There are only atoms and ionized atoms there. Are there any known pathways by which we can describe how aromatic molecules like benzene rings and the biga came in presence in the ISM? It's a very good question. We don't know very well these processes, but the current idea, and Alexander Tillens might talk about it, is that they form in the expanding shells of the dying stars that already formed a carbon in the interiors, and this carbon got mixed up. They have specific masses. They can produce a lot of carbon, and so they have like very carbon-rich outer shells. And if they're expanding, because of the expansion, they are adiabatically cool. And this carbon, because there's still hydrogen around, get converted to hydrocarbons. And then there have been proposed mechanisms how from these hydrocarbons we could form acetylene, C2H2, and then by insertion reaction via neutral reaction pathways, which can occur in these outer shells because they're still, let's say, 1,100 degrees Kelvin, maybe 3,000, 2,000, whatever. And so that you could still, by neutral reactions with barriers, you could still form the benzene ring, C6H6, and then they can grow further. But then eventually this stuff gets expelled into the gas, as the gas, or maybe as the solids into the stellar matter, and then these polyaromatic hydrocarbons might grow further by gas phase processes there. I mean, is the redshift in wavelengths of light indicate the heavy molecule? No. The redshift is only a measure of the distance, so to say, which is equivalent to the age. This redshift is because the universe is expanding, and the further the object away from us, the faster the velocity with which it flies from us, from our center of, let's say, a baryonic center of the solar system. And then if you know that, okay, you are looking at the light of, like recombination light for hydrogen, then the specific one, the frequencies from the lab and from the quantum calculations, and the redshift, then okay, that's the redshift, which means the distance, which means also the age of the universe at that moment. Are there other methods other than transit methods to detect exoplanets? Excellent question. Thank you. Transit methods plus radial velocity methods are the most commonly used one. And radial velocity methods, imagine you have a, let's say, massive planet far away and the star, but the planet doesn't transit, so we don't see the dips in its light curve. But if it's massive enough, it cannot it can pull off the stars so that, you know, like they rotate along the gravitational center of mass, which could be away. It is usually not centered in the star. For some small planets it is, but let's say if it is off star, then it would, and if it's nearby, so we can detect its motion on the sky with time, it could appear like it's wiggling about, wiggling around the kind of straight line. This wiggling could indicate the presence of the companion. It could be another star, sometimes it could be a heavy planet. That's the radial velocity method. Another way of doing that is to look into the spectral feature, atomic features in the stellar atmosphere, and if there's a planet around which is not transiting, it can also pull off the star back and forth. So these lines would also kind of wiggle back and forth. This is a radial velocity kind of method and so on. Yeah. Do we have still time, by the way? It's already 5:05.
We can, in principle, extend a bit this lecture. We don't have really very strict.
Okay, good. Because there are some nice questions. There is a question: how does one interpret the information in the images obtained using 12 CO versus 13 CO or C18O emission? It's an excellent question. I had no time to talk about it, but CO is made of carbon and oxygen, and carbon and oxygen have stable isotopes besides 12 carbon and 16 oxygen. And abundances of these minor isotopes are much less than 12 carbon, let's say in the case of 13 carbon, and 18 and 17 oxygen isotopes are much less abundant than 16 oxygen, main isotope. And you could still combine CO monoxide molecule out of these isotopes, but they will have much smaller abundance compared to 12C16O abundance. By that manner, the emission would have different intensity, and you can look, for example, in protoplanetary disks, and Catherine Walsh will be talking about it, and Ted Bergen probably as well. You can use this various carbon monoxide isotope logs to look into the disk, into the different regions, because 12 carbon 16 oxygen main isotope log emission saturates very quickly, so the emission comes from like more outer part of the, for example, protoplanetary disk or dense cloud, but C18O emission or certain CO emission is much more transparent and traces like more dense, more central parts. This is an excellent question. Thank you. How do you know whether a molecule is formed using radiation chemistry or photochemistry? I mean, it's a good question, but in principle, most of the reactions in the interstellar space is ion molecule reactions. But then you could have an idea about also about the physical conditions nearby, because you can see it in the visual wavelengths in the optics with the telescopes, normal telescopes. And you can see, is there a like massive, highly ionizing star around? If it is around, you may expect a lot of the stellar ultraviolet photons coming and affecting the gas nearby. And then you can imagine a lot of molecules would be affected by this highly ionizing and dissociating radiation. And then, of course, only specific types of molecules would be stable at that condition. And we usually see this correlation because we kind of nowadays understand these astrochemical processes, at least for relatively simple molecules, are quite well. And we can understand, okay, this specific molecule, especially if it's molecular ion, probably is formed because the precursor molecule or the molecule itself has been affected by the high energy radiation, something like that, yeah. Let me see what else. There were tons of questions. Thanks, by the way, dear student, for being so active. You far exceeded my expectations. I thought it's like remote lecture in Zoom could be boring, you know. I'm really glad that you had so many questions. Let me see what else. Why is there not a great amount of lithium-containing chemical species in the interstellar medium? Very good question as well. Lithium, and to some extent, is deuterium, especially deuterium, because it's mainly formed as hydrogen and helium during the Big Bang nucleosynthesis, but also partly lithium. They're both of them, they're being consumed in the nuclear fusion reactions. Lithium, I think, can be formed as well in the stellar nucleosynthesis, but it is formed, but then it's like an intermediate product, and then it's being used in other nuclear fusion reactions. And actually, it's interesting that amount of deuterium in local universe around us, like in Milky Way, in the nearby galaxies, is a bit, I think it's roughly twice times less than how much it was right after the Big Bang and when the Big Bang nucleosynthesis has stopped. So half of all deuterium in the universe have been processed, I think, inside stars by the star formation. In a reaction network, what factor affects the importance of a particular reaction? It's another good question. It's usually for the reactions in space, especially in the interstellar space, which is cold, it's the presence of an energy barrier. If there is a substantial energy barrier, then we know that easily that this reaction, albeit it may be very efficient, very important, under the Earth's atmosphere conditions, will not work, or will only work in a warm gas around freshly formed stars or in protoplanetary disks in the inner parts. It's usually energy barrier, but then also there are some other factors, but there is not such a straightforward answer. Often enough, one has to run a chemical model and then analyze what are the chemical processes were the most important ones for the formation and destruction of this specific molecule or an atom of interest to understand. Okay, these were the most important reactions, and the rest, albeit they were in the network, were included in the models. They haven't contributed much to its formation and destruction, therefore they are unimportant. But yeah, let me see what else. Why deuterium was produced not during the Big Bang as sometime after, and this time was, by the way, was between 10 seconds and about 20 minutes. The reason for that is, in essence, why it was like offset from the exact time zero, so to say. It's just that the physical conditions at the time before 10 in the first 10 seconds were too harsh for deuterium to be stable. So essentially, the strong nuclear force binding together, proton and neutron in the deuterium nucleus, the background temperatures and the radiation was just, the energy essentially was bigger than that. So albeit the protons and neutrons themselves, they've been stable, as well as electrons and positrons, but the combination of proton and neutrons, like the simplest one is deuteron, the conditions, at least before the 10 second was over of the lifetime of the universe, they were too harsh. Talking about the reaction barriers, would the radiation energy be used to overcome the barrier to facilitate the reaction? Oh yeah, absolutely. Actually, it's a wonderful question. I mean, this external radiation, it's especially profound for the icy chemistry. Essentially, the surface reactions that occur in the cold regions where many molecules in the gas phase can stick to silicate or to carbonaceous grains. And usually it happens in the dense environments where there's still a lot of small dust present, blocking, the UV light from coming, but cosmic rays can penetrate. Sometimes they can excite the local hydrogen molecules and produce the secondary electrons, and then the secondary electrons colliding with another molecules and elements produce the secondary ultraviolet radiation. These ultraviolet photons can facilitate, for example, the cold icy chemistry and create really complex organic molecules very efficiently, even if the temperature of the grain is like only 10 Kelvin, and the molecules that are frozen there, they're not moving that efficiently. That's wonderful question. Thank you. A bit philosophical question. What was there before the Big Bang? Any hypothesis on that? I don't really know. No one really knows, actually, because it's essentially a singularity out of which we have emerged. It's hard to say what was before the singularity. I think there could be some pure theoretical cosmological ideas, but I'm not really very well versed in that. Is the reaction rate of certain reaction faster than in space from Earth or from Earth? It depends on the reaction. As I said, the reactions with substantial barriers, they're of course happening in the Earth's atmosphere or in the oceans or in the seas, but they're not happening in space. On the other hand, some of the reactions, some of the radicals like helium H plus or CH plus that have been found in space and detected, it's a pain in the back to form it in the laboratory, because even in the ultra high vacuum laboratory setups, the background particle density is so high, still more higher than interstellar space, that these radicals, they would react with something else and never be present in detectable amounts. And for these specific reactions, that usually is kind of probably more efficient to some extent in terms of creating interesting molecules that are more efficient in space than the Earth, are these radiative association reactions. Is when two atoms, heterogeneous atoms, collide and form a molecule, diatomic molecule, molecular bonds. These reactions are very slow, for small elements, for atomic elements, these reactions are very slow, and they don't really occur. They are improbable under the very dense Earth-like conditions, but they very rarely occur in space, and space is big, and space can wait many millions, tens of millions of years, and in this way you can create exotic radicals by these very improbable reactions from Earth-centric point of view. Why do we have in asteroids belts carbonaceous chondrites? Why they don't participate in planetary formation? What are the limiting factors? Another very good question. As far as I understood, nowadays, this asteroid belts and Kuiper belt as well that we have a bit further away in our solar system. Asteroid belts is something between, this kilometers to several or 1,000 kilometers in size. Bodies orbiting between, roughly speaking, between Mars and Jupiter. And these are the remnants of the planet formation in the solar nebula 4.567 billion years ago. It's something that remained. Sean Raymond and Alessandro Rabdelli will explain it more clearly, but it's something to do with how Jupiter, it's the most massive planet in our solar system. It formed probably the first, and because it's so massive, it affected the formation of the other planets around it, and also blocked the transport of matter from the outer parts of the nebula towards the sun, where the Earth-like planets have been forming. And and also disrupted because it also could have moved a bit radially from more further out distances towards the sun. It could have disrupted the formation of another planet, and its building blocks kind of got scattered and partly remained even after the solar nebula itself. The gas there got dispersed and the planets have been formed and the orbits have been fixed. But I feel it as the remnant from the formation of the solar system itself. And carbonaceous chondrites are interesting because these asteroids that formed slightly further away from the sun, and they are composed, they've been composed from solid matter, but a lot of ices, including very complex organic species that we found in space, and also we see them in comets, but also in other stuff in regions. And then these carbonaceous asteroids, some of them could have been fallen, and much more of them have been falling onto the very young Earth, and they could have delivered the organic stuff that was formed also inside of them, because some of them were big enough to have warm enough interiors to melt water ice and have a liquid water. And the density of liquid water is much, much higher than, the densities of liquids are higher than the densities of the gas. And therefore, chemical reactions have been much, much faster there. And we know it from the analysis of carbonaceous chondrites on Earth that they contain a lot of prebiotic stuff, fatty acids, out of which lipids and membranes of the first cells could have been made, amino acids, then nuclear bases and sugars and all the other stuff. In that sense, yeah, they could have been important for the original life. Alexei Potapov probably will talk about it. I think one has to also talk about quantum mechanical tunneling, which plays an important role in promoting chemical reactions with activation barrier. Absolutely true. I have forgot to tell that exactly. When hydrogen-bearing molecules or radicals collide, some kind of reactions that occur could involve just a tunneling of one, let's say, hydrogen proton from one reactant to another. And then, of course, the tunneling can overcome the barrier more efficiently rather than it's done mechanistically. It's actually interesting that the quantum tunneling is also the reason why, the sun shines. It's also like the starting reaction, or one of the reactions in this proton-proton chains involve a tunneling of a proton over the nuclear reaction barrier. Yeah, I forgot to mention that, but this tunneling is also it's important for chemical reactions. Yes, absolutely right. Do you think complex molecules can form in gas giants like Jupiter and Saturn? Yeah, I think they've been found there, yeah, I mean, especially in the atmosphere of these giants, because they are radiated by the cosmic rays from the interstellar space, by the stellar light as well, by interstellar UV radiation. There's always kind of a background ultraviolet radiation. And because we have a lot of this carbon, nitrogen, oxygen, sulfur, and so on bearing molecules in these atmospheres, unless these are very hot exoplanets, yeah, I mean, you form via photochemistry very complex stuff. Even like in the atmosphere of Titan, it's the largest satellite, right, of Saturn, where the lander, Cassini-Huygens lander, has landed. The Titan has an atmosphere almost like Earth-like, and to reach, I think it's about like 1 bar pressure, maybe a bit more. And because of the photochemistry, we found very, very complex hydrocarbons and organic hazes, which are really macromolecules in its atmosphere. Yeah, so it's absolutely, photochemistry is a powerful thing. It's the question about the neutrino image from the Super Kamiokande experiment. The question is, the size of the wind-rich area shouldn't be larger than the size of the sun, right? If the plot shows the whole sky, why doesn't the wind-rich area takes up such a large portion? Oh, it's a wonderful question as well. It's the problem of angular resolution, which we have to always deal in astronomy. Even optical telescopes, because of the limited size, have a limited angular resolution. So there is always the tiniest element on the sky, which you cannot see the details inside. It's like a pixel, roughly speaking, if you can imagine that. And for the neutrino experiments, like detectors like Super-Kamiokande, they're not very accurate because there is no mirror. Because Super-Kamiokande, it is located in Japan, in the almost 2-kilometer deep gold mine, in the bottom of this gold mine. And it is essentially a huge cistern of distilled, very pure water. And the walls of this cistern are covered with photomultiplier tubes. These are like detectors that can detect the light. And what they are detecting essentially is the neutrinos interacting with the water molecule and kicking out electrons sometimes from that. And these electrons, because they have relativistic energies after the interaction, and the speed of light in water is shorter than the is slower than the speed of light in the vacuum. But these electrons, they initially have this kind of almost speed of light in the vacuum. They create what's called Cherenkov radiation, and that's what these photomultiplier tubes are detecting. And they kind of can reconstruct the direction from where this neutrino came from, but it's not very accurate. That's why this illuminated area where the neutrinos come from is like almost half of the sky, or at least quarter of the sky. That's because the resolution of this kind of, it's not even a telescope, it's a detector, is bad. That's why. All right. I'm really thankful to you guys. I mean, we had a really nice session, almost 40 minutes I'm answering. That's amazing. Thank you all.
Yeah, thank you, Dima, very much for excellent lecture. And I also want to thank all audience for being very active, and I hope this will hold on for forthcoming lectures.
Thank you, Sergey, for moderating this session. Dear students, please consider coming for the next lecture. It will be very interesting. It will be about the origin of the universe. Think about it. It's not just interstellar matter. Who cares? It's the origin of the entire universe. And this very cool stuff happening, the extreme physical conditions. All right, thank you again. Yeah.
Yeah, thank you, everybody. Yeah, with this, I think we will finish today's lecture. And bye-bye to everybody.
Bye-bye. Have a nice time of the day, evening, day, or morning, depending where you are. Okay, bye-bye.